So the second video is for the section 1.3 notes. So yesterday we were dealing with looking at functions, finding domain and range. We were evaluating functions by plugging stuff into the equation. Looking at intervals, that interval notation, and we're going to come back to that interval notation again today. So these notes are going to focus around intervals of increasing and decreasing. So as we're looking at this graph, where is the graph going up and where's the graph going down? And we can describe that using intervals. We'll talk about maxima and minima, basically mountain peaks and valleys on these graphs. And then finally we'll talk about whether a function is even, odd, or neither and what that means to have. So first thing we are going to look at is intervals of increasing and decreasing. Now there's an extra slide that you have on your handout that isn't on here. That slide talks about some things that deal with increasing and decreasing. So first, we always read from left to right. Always read from left to right. And you might even throw a little note in there that when we do increasing and decreasing, we always look at the x values. Always, always, always. When we're doing increasing and decreasing intervals, we don't care about the y values at all. When we use intervals to describe increasing and decreasing functions, we only look at the x values. We start increasing at this x value, we stop increasing at another one. So left to right, only looking at the x values. We'll look at the y values with something different next. So then we need to look at our graph and figure out where does it start to increase and where does it stop increasing? Or where does it start decreasing and then where does it stop decreasing? And that's what's going to help us figure out that interval from where to where. What x values are we looking between? And you can kind of think of this like a roller coaster where left to right we're either going up a hill or going down a hill. Don't look at where the arrows point. We'll see that on this first example here. Don't look at where the arrows point. We start on the left and work our way to the right. And then finally, the last thing we need to know is that we always have open endpoints. So we never have brackets when we're dealing with these intervals of increasing or decreasing. And I'll explain why in a little bit. So let's look at this first example here. We have a graph. It looks like it's made up of 3 different line segments. We want to describe where it's increasing, where it's decreasing, and where it's constant. So let's start with increasing. Now read left to right. We notice that it starts increasing somewhere down here, and then it's going up in that direction. Just make this a little thicker. There we go. So it's increasing right there from left to right. So where does it start increasing? This is kind of a tricky question because it starts at negative infinity. It's not that it doesn't start at -9 or -10. That arrow on the bottom left means that we are going forever to the left, which means starting at negative infinity, going left to right, we are increasing all the way until we get to this point up here, that mountaintop. Once we get to that mountaintop, we stop increasing. So here, let me erase this so you can see it a little bit better now. So we start increasing down here at negative infinity, and we increase all the way until we get to that mountaintop. So what is the x value of that mountaintop? We start at negative infinity, and we increase all the way until x is at -2. So from negative infinity all the way to -2, this graph is increasing. Then we also said that we always have parentheses. We can never equal infinity. And then with the -2, look at -2, that top of the mountain. At that mountaintop, is it increasing? When you're at the peak of a mountain, can you still go up? No, you're done going up, and you could go down one way or down the other way. but you're not increasing anymore. And that's why we have to stop at that -2, but we can't include it. Because at -2, which interval are we really in? Well, we're not in an interval, we're at the top. So it's not increasing anymore. Then decreasing. At that x equals -2, that same x value, where we stopped increasing, that's where we start decreasing. So we start decreasing here at -2, and we decrease all along this line right here until we get to +2. Once x equals +2, we stop going down. We hit that level slope on the bottom. So from -2 to +2, it is decreasing. But we have to use those parentheses because at -2 and at +2, we're not increasing or decreasing. It just is. It's there. That's the transition point. So then where is it constant? Well, it stops decreasing at +2 and it starts going just straight across. So from 2 all the way until x equals infinity, we have a constant graph. So increasing, -infinity all the way up to 2. Then we decrease from x equals 2 to x equals, or -2 to x equals +2. And then at x equals +2, we stay constant all the way to infinity. So we're using these intervals to tell us, to describe where this graph is going up and down. So you'll do a little bit of work on intervals on your worksheet today. The next, we're talking about maxima and minima. So we have a relative maximum at any point where the function changes from increasing to decreasing. Now it's very important that we use that definition. It has to change from increasing to decreasing. It had to go up and then turn around and come back down. Then we have a maximum. Similarly, with a relative minimum, we have to change from decreasing to increasing. If we change from decreasing to increasing, then we have a minimum. A mountaintop versus a valley. So the increase-decrease is important because if we just had like some function with an endpoint right there, this endpoint cannot be a relative maximum because it's not changing from increasing to decreasing. Now it's part of the range, and that would increase our range, but it's not a mountaintop because it didn't change. So weird definition there that we need to be careful of. When we talk about a relative max or a relative min, we need to use this kind of description. That we say the maximum is this y value. This y value is the highest point it goes to, and it happens at x equals something. So we say the y value at x equals whatever. So you're giving the height of the mountain and then the location of the mountain. So let's look at an example here. So this graph, before we look at what the relative max and mins are, we can count how many we have. So relative maxima, the places where we have a mountaintop, it changes from increasing to decreasing, we have 1, and it's right here. Relative minimum, we have 2 of those. There's 1 down here and 1 down here. So there's 2 or 3 different points we have to describe. So to describe the relative maximum, this point up top here, we have to count those lines to figure out the highest y value. So that's about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the relative maximum is 10. That is the highest peak, the highest point that that peak reaches. So the relative maximum is 10, and it happens at x equals, and this is where we want to look at the x value, and it happens to be at x equals 3. So the relative maximum is 10 at x equals 3. Then we can look at the relative minimum. we have two, and we have to describe both of them. So the first one, let's do the one on the left. Doesn't really matter what order you do it in. But first, look at the y value of that point. The y value is down at -6, so our minimum there is -6, and it happens at x equals 1, 2, 3, x equals -4. So the minimum is -6, and it happens at x equals -4. The other minimum over here is actually at 0. 0 is the y value there, and that happens at x equals +8. So two minimums, -6 and 0. The -6 happens when x is -4. The 0 happens when x equals +8. So that's how we find maximum and minimum. So I think on your worksheet you have 4 problems where you have to go through and describe the intervals of increasing and decreasing and the maximums and minimums. And it's actually kind of a difficult thing for some kids to be able to put all of that together, to see what part of the function we're really talking about for those increasing, decreasing pieces. Also notice that the increasing and decreasing intervals start and stop at those maximums and minimums. There's a question on your worksheet that asks about that. So think about that. The minimums, maximums, they happen where the intervals start and stop for increasing and decreasing. All right, next, the next piece, the last piece we're dealing with, are odd and even functions. I'll be honest with you, odd and even functions are in a lot of ways more of an interesting piece of math rather than a vital piece of math, but it does give us some interesting insight into what some of these functions are like. So anytime we have an even function, notice at the very top here, we have f of -x equals f of +x. This is the definition of an even function. It has that property right there. So it means that if you have some function, if you plug in +2 and -2, you will get the same y value. If you plug in +10 and -10, you will get the same y value. If you plug in +3,682 and -3,682, you will get the same y value. So the positive and the negative x have the exact same y. What this essentially causes is a reflection over the y-axis. Because when you take all the positive x values and you just reflect them, so take all these and reflect them to the other side, the y values match up. You take the positive x and the negative x it reflects to, they have the same y value. So even functions always have that symmetry over the y-axis right here. So if you're given the one half of the graph, all you have to do is reflect the points to the other side and you'll get the other half of the graph. One thing to think about with that then is if you have a point xy on the function, if it's even, then the point -x, -y is also on that function. Or sorry, -x, +y. So if xy is on it, then -xy is on it. X and -x have the exact same y value. That's an even function. Now we should be careful when we talk about even functions. You notice this one's a parabola, y equals x squared type of function. Not every parabola is an even function. If we start shifting the parabola left and right, now it won't have that same reflective property. So be careful about those. Always look for that symmetry. Next we have odd functions. Now odd functions are a little weird to define this property, but if you plug in an x value, you get out a y value. A function is odd if you take the negative x value and it gives you the negative y value. For example, if the point 2, 7 is on the function, if the function is odd, it also contains the point -2, -7. So this makes the x and the y negative. So if the point 5, negative 3 is on the function, then the point negative 5, positive 3 is on the function, if it's odd. So we change the sign on both the x and the y. What this causes is a symmetry around the origin, like a rotation like a pinwheel. Now, if you're given half of an odd graph, if you're given half the graph and you're told, hey, this is odd, then look at the points x, y, and just change the sign. Makes them negative x, negative y. Or if one's already negative, make it positive. So just switch the sign on both of those. And that will tell you what new point is going to be on your graph. So you have a few problems on your worksheet where you have to do this kind of thing. So that's even and odd. If there is no symmetry, no rotation, no reflection, then it's neither. It's neither even nor odd, which is perfectly okay. There's an infinite number of functions that are not even or odd. So a general guideline then, we can find even and odd functions without looking at a graph. So we don't need to visually see it in order to decide if it's even or odd. All we simply need to do is find the f of negative x. Right? If we look back, as we saw before, if you plug in the f of negative x and you get the exact same output as f of positive x, then it's even. If you plug in f of negative x and you just get the negative y value of it, then it's odd. So we can plug in f of negative x and evaluate and see what happens. Now, you're not going to end up with just a number as your answer. You're going to end up with a function that still has x's in it. So we need to follow a few guidelines. If you plug in negative x, simplify, and nothing changes, the function is even. Because you plugged in negative x and you just got the exact same function, the exact same y value. If you plug in the negative x and it changes all of the signs, it takes the original function and just makes everything negative, well, you just took the y value and made it negative. So all the signs have to change. If you plug in negative x and the signs don't all change, it's not the same, but it's also not totally different on the signs, then it's neither. So for example, I think yours has this on a different slide, but for example, we have f of x equals 2x. So now let's find the f of negative x. The f of negative x equals 2, and instead of positive x, we'll replace it with a negative x. But 2 times negative x is just negative 2x. Do you notice how this is the negative version of the original function? F of x is 2x, f of negative x is negative 2x. By making the x value negative, we made the y value negative. When that happens, this is an odd function. Same functions, but all the signs changed, which was only one sign. So let's just do 2 more examples of these, and then you can spend the rest of the time working on your sheet. So tell whether the function is even, odd, or neither. So we have f of x equals 2x squared plus 5. So to decide if it's even, odd, or neither, we need to find the f of negative x. Which in this case, instead of 2x squared, we'll do 2 times negative x squared plus 5. So we just plug negative x into the function wherever there was a positive x. And now we can simplify. Negative x squared, that's 2 times negative x plus 5. Now we need to remember how squaring works. If we take a negative x times a negative x, those negatives are all going to cancel out and just become positive. So we just get 2 times x, which is 2x squared plus 5. We plugged negative x into this function, and it didn't change a thing. That is an even function. We plugged in negative x, we simplified, the negatives canceled, and nothing changed. All right, one more of these. So tell whether the function is even, odd, or neither. We have x squared plus 2x plus 1. So you take a minute and try this one. The f of negative x, what is that equal to? So if you need to, pause the video, try that problem out, and then start it up again and I'll do the answer right away. So we have negative x squared plus 2 times negative x plus 1. Well, the negative x squared, we saw that on the last slide. The negatives are going to cancel, and that's the same as positive x squared. Not too bad. So it's on the track to maybe being an even function. So 2 times negative x is negative 2x, and then we still have the plus 1. So is this the same as the original function? No, it's not actually. The original function had a plus 2x, our new function has a minus 2x. Those aren't the same. This is not even. Well, if that sign changed, did all the signs change? If all the signs changed, it's odd. So we have the 2x and the negative 2x, but nope, a plus 1 and a plus 1, a positive x squared, a positive x squared. The signs didn't all change, only that one. And so this isn't odd either. So this is neither. There is no symmetry either rotating around the origin or reflecting across the y-axis for this graph. So try and finish up that worksheet using the ideas that we're talking about in these notes, and come with questions on Wednesday when I come back, so that we can make sure that everything is answered before we move on to some new stuff.